when it first came out. That's right, natural selection. So get that level. There we go. Okay, so today we're talking about stationary points, and this flows directly from what we did in our last lesson on Tuesday. On Tuesday we were talking about when we have a positive slope, that means the function is increasing, and if we have negative slope, that means the function is decreasing. So what we're going to do today follows directly from that. Just to do a summary of stationary points here, this table is a very important table and we will refer to it. All right, we're familiar with a local max, okay, so it's a point in the graph where there's a peak. We have a local min, which is a trough, all right, and then we have these new points that we're going to learn more about probably in 3D.1 and 2, but we'll get some exposure to now. It's called a stationary point of inflection. And what's going on there is the function is increasing, it goes horizontal. Horizontal means the slope is stationary. It's not increasing, it's not decreasing. So it's increasing, goes horizontal, and then keeps increasing. Or the opposite case, we can have decreasing, goes horizontal, and then keeps decreasing. Those are both called stationary points of inflection. They're not local maximums, they're not local minimums, they're points of inflection. And I think I'll just talk about the relevance of what that is tomorrow, but for now it's just it's a point on the graph. Okay, so here we have our first function, and let's get straight into the example to draw out what's going on. So the process is going to be the same. What we're going to do is find f dash of x and draw its sign diagram. So if we differentiate this function, we will get 3x squared take away 6x. Now, I'm going to make a manual argument for this one on how we can draw the sign diagram because it's quite easy for us to do. What we need to know is the roots. The roots occur when the function is equal to 0. We can factorise 3x and apply the null factor law. So that means on our sign diagram, the roots are 0 and 2. All right. And we also know this function that we've drawn the sign diagram for is a quadratic, okay? The leading power is 2, and it has a positive a value. That means the coefficient of x squared is positive. Now remember, if a is positive, we're smiling, we're happy, and if a is negative, it's going to be a sad face. So that means this quadratic is opening upwards, so we're going to have plus, minus, plus. That's the sign diagram of the first derivative. Okay, now what this tells us about the original function, remember this is the slope function of the original function, right? So it tells us we have positive slope until we get to 0. All right, so we have positive slope, so we're increasing until we get to 0, and then we're decreasing, then we have negative slope. So if we move from positive slope to negative slope, from increasing to decreasing, we have a local max. All right, so what we can see here from the sign diagram is we have a local max when x is 0 on the original function. So we have a local max at x is 0. The corresponding y value, we put this x value into the original function. When x is 0, the y value is minus 2. Okay, similarly, we have negative slope, it's decreasing until we get to x is 2, and then it's increasing, surfing, decreasing to increasing. So we have a local min at x is positive 2. To find the corresponding y value, we're going to put 2 into the original function, or we've graphed it, just g-solve. Okay, so all of this you can answer from the graph, but we're using calculus techniques. So we're showing them working, and then we can use our graph to help us generate. So we can see the local max there, x is 0, y is minus 2, and we g-solve the minimum, x is 2, y is minus 6. You can put it in here if you want to, but it's much faster just to g-solve it. Your calculator is your friend. Those are the two stationary points on this function. Okay, cool. Let's move on to the second one then. Actually, maybe I'll just make one connection quickly. So we're using the derivative function to tell us about the original function. And remember, we can use our calculator just to sketch the derivative of this. So if I'm doing it on Desmos, what I'd do is type in f dash of x. Get there? All right, I'm going to turn the original function off. So this is the derivative function, and we can get the sign diagram even from our graph. We don't have to perform this manual process, okay? We can get it straight from our graph. Here I'm just demonstrating those mathematical techniques that we have covered back in year 11. Okay, now let's move on to B. Here we have a function. It's x take 2 multiplied by x plus 3 to the 3. So we can start by sketching it, and we can observe the stationary points immediately. So let's all go in and sketch that. We have x take 2, x plus 3 to the 3. And then it's plus 4. X take 2, x plus 3 to the 3. That's 4, good. And I'll turn off the first derivative. And it's going down a fair bit, so we'll need to zoom out for y. Let's crank y to minus 100, or minus 80. There we go. We can see it a bit better. All right, so just looking at the graph, we should start to be able to pinpoint where the stationary points are. So stationary points occur when the function is horizontal. That's right, there is. So it's going like this, isn't it? And then it goes all the way down here, and then there's a local. So this graph has two stationary points, all right? Stationary points when the slope is 0. It's not increasing, it's not decreasing. Very clearly we have a local minimum there. We can g-solve that. What you can't g-solve on your calculator, there's not a function for, you can't g-solve points of inflection, okay? But we'll reveal a number of strategies about how to use your calculator to find them using the first derivative and so forth. All right, so we have a stationary point there, the slope is horizontal there, and the slope is horizontal there. We're going to find both coordinates, and we have to state the nature of these turning points. That means, is it a max, is it a min, is it a stationary point of inflection? Okay, so let's use the calculus techniques. And the way we use the calculus techniques is we differentiate, we find the first derivative. In order to differentiate this, we need to use the product rule. Smash it all together. All right, now this function here, that's the derivative function, and we can just graph it and get the sign diagram from there. But I do just want to draw out one algebraic skill here that will pop up, particularly in this unit, is a way to simplify a function like this. Okay, we should be looking at that and going x plus 3 is common here and here. In fact, it's squared here and it's to the power of 3 here. So we're going to pull that out the front. All right, and what we would have out the front is we have x plus 3 squared out the front. And so then that leaves us with one lot of x plus 3 here, and then x take 2 times x times 3 here. Okay, now for this one here, I'm going to expand that and collect these like terms so that that's a single linear factor as well. And I'm going to make a connection for you guys. So we have the x plus 3 squared out the front. We'll leave that as x plus 3 for now. This becomes plus 3x take 6. And we'll get 4x take 3. Okay, I think the only tricky part there is seeing that x plus 3 is common and pulling it out the front. Again, the checkpoint is to go, if I now expand this, would I get what we started with? And the answer is yes. We've got x plus 3 to the 3, and there we have the x plus 3 squared term there. Okay, now what's good about this is if we're looking at this function, we should see we have a linear factor multiplied by a cubic. So that means the highest power is x to the 4. Okay, this is a quartic function, and we know when we differentiate a quartic function, we get a cubic function. all right? So we have a double root and a linear root for this cubic function. All right, and so we can even see the roots from here. All right, the roots occur when the function equals 0. We have a root at x is minus 3. All right, so if I write, let's do the null factor law first. If we make it equal to 0, we have x is minus 3, or we'll solve this one, x is 3/4. So for our sine diagram, minus 3 and 0.75, 3/4. And if we have a cubic function, cubic functions, we have, if it has a positive a value, it has this shape, and if it has a negative a value, it has the opposite, which is like that. You're not expected to remember that, okay? That's something you would have covered in year 11. But I know, okay, if we have positive a value, this is what it looks like. So it's going to come up, touch, come back down, and then cross there. So it's going to be negative, negative, positive. All right, so I know that from 11 methods, but let's show you how we can get that from our calculator. We've sketched the function. We know if we sketch the derivative function, all right, this shows us when the slope is horizontal. It's going to be horizontal here at x is minus 3, and horizontal here at x is 0.75. That's what we've found using the factorization techniques. We can get that straight from our graph. Use your graph to help you. But the point of this function is it's below the x-axis, it touches at minus 3, it's below the x-axis, it crosses at 0.75, and then it's positive. Okay, so this is the sine diagram of the derivative function. And we're going to use this to make statements about the turning points on the original function. The first one's easy. We have a local min at x is 0.75. Let's find the corresponding y value. All right, now be careful. People make mistakes here. They find the y value on the derivative function. We don't want that. We want the y value on the original function.
So we have to be able to tell the mins, maxes and stuff, you just put in your calculator.
Sorry?
To be able to find the local mins and maxes.
Yeah, just G-solve. Absolutely. Yep, that's what I encourage you to do. Yep. You can't G-solve the point of inflection though, so you will need to rely on your calculator a little bit there. So we have a local min here. Now we can see from the original function that it's decreasing, goes horizontal, and then keeps decreasing again. So we know this is a stationary point of inflection. All right, and we know that it occurs at minus 3. Find the corresponding y value when x is minus 3. The y value is, we can type it into the original function or G-solve it, positive 4. Okay, so what we've done there is we've found the coordinates of the turning point. That's the coordinates. And then this is their nature. What's their nature? It describes what kind of turning point it is. All right, so that's really good. I feel like there was one more thing I wanted to mention with this one. So we can get the derivative, G-solve those points. Oh, okay, it's just this point. Okay, it's just this point that if ever you see on the sine diagram of the first derivative minus minus, that means stationary point of inflection. Just as negative positive means local minimum, decreasing then increasing. Well, what this means is that it's decreasing, goes horizontal, and then keeps decreasing again. So that's a stationary point of inflection, and so is, as is stipulated in the table, this one. Okay, increasing, goes horizontal, and then keeps increasing. So whenever they're the same about a root, stationary point of inflection. Okay, good. Let's look at our last example, and this is going to be a good one for us to draw out periodic solutions. So this is something that popped up, not in the previous test, but in the previous practice test that I said we would address in later lessons. So we have the function f of x is sine x. Okay, so we're going to graph we're going to draw the sign diagram of the derivative function. So the derivative function then is cos of x. And I'm going to sketch it between 0 and 2 pi to begin with. And then we'll talk about solutions outside of this. Because we know cos of x is a periodic function. That means it's going this way forever and this way forever. The reason I'm restricting it between 0 and 2 pi is that this is one wavelength of the function. So we need one wavelength to find the solutions, and then the others are just going to be repeated solutions of that. Okay, so the roots of cos x, all you need to do to find this is just be a bit intuitive about it. This is your unit circle. We want to know, when does cos x equal 0 to find the roots on here? Well, cos x is the x coordinate. The x coordinate is 0 here and here. So the angle, pi on 2 and 3 pi on 2. All right? And even then, like, we can refer to our graph. Yep, you can, that's absolutely fine. But let's see if we think about it. Like, for between 0 and pi on 2, if we're going around the unit circle, those values have a positive value of x. Then over this region, we have a negative value of x. And then after that, we have a positive value of x. Now let me just refresh you how we can use our calculator for it again. So I'll go to sin x. We can sketch the derivative function, which is cos x. Let's change our v window a little bit. So I'm going to sketch it between 0 and 2 pi, minus 1 and 1, 0 and 2 pi. Okay, so that's what the cos of x function looks like. We can see our root, pi on 2. All right, remember pi is a number, 3.14. 3.14 divided by 2 is 1.57-ish. All right, so it's just a number. Now what you can see is, if I zoom out, is that it repeats itself in both directions. So what that means is this stationary point is going to repeat itself every wavelength, and this stationary point here is going to repeat itself every wavelength. Now, wavelength, okay, good opportunity for us to recap that. If we have, let's do it in the simplest form, the sine of bx, the value of b tells you how many wavelengths there are in 2 pi. That's always the case. Here we have a value of b of 1, which means we have one wavelength in 2 pi. That's why I've restricted the domain from 0 to 2 pi. Okay, so our answers are, remember we're using this derivative function here, sign diagram, to make statements about the original function. The original function, sine of x, has a local max. Okay, a local max at pi on 2. I'm going to leave a big space there now. And the y value on the original function, when x is pi on 2, the y value is 1. Now, of course, this is the case. Again, think of our unit circle. All right, when we get to here, all right, the cos value, the x value is 0, but the corresponding y value is 1. Okay, so the maximum it can be is 1, and the minimum that it can be is, all the way around here, minus 1. Now, what we need to include in our solution is every possible answer. And so what we're going to write, or introduce you or reintroduce you to this notation, plus k2 pi. Plus k2 pi. Where, or for all, k is an integer. I'm going to explain all that notation. You don't have to write it like this. This is the mathematical way to write it. If you wanted to write it in words, you could say for all integer values of k, or something like that. Okay. All this means, just in terms of the notation here, for all, okay, so it's like an upside down A, or it's like that. For all K is the value that we've introduced, so K is a variable. Epsilon means belongs to, Z means the set of integers. Integers are whole numbers, 0, 1, 2, 3, 4. So what it means is we have local maxes for all values of pi on 2 plus multiples of 2 pi, plus 2 pi, plus 4 pi, plus 6 pi, plus 8 pi. All right, all values of K, integer values, allow you to have a multiple of 2 pi. So here's the first max, right? Let's go to the original function. Okay, so the first max occurs at x is pi. Let me make the argument like this. X is pi on 2, sorry. X is pi on 2. The next local max occurs at x is pi on 2 plus 2 pi. The next one, plus 4 pi. Okay, because it has a period of 2 pi, and so each point is going to repeat itself every 2 pi. So what we've done there is answer every solution. Most of the time you'll have a constraint for a periodic function. Most of the time I'll say find the local minimum and maximum between 0 and 2 pi, but here we've allowed for every possible solution and explained that notation. All right. Any questions about this process here? Really good. So we'll let you guys crack right into it. I'll just show you something I've got for you today as well. Hopefully we can go over another conjecture question at the end of the lesson for stationary points. And then we have a booklet for you on conjecture questions. Got like 16 of them in here for you to practice with. So